Good morning, everybody. I think we can get going now, and welcome to this webinar today, Software for Woodworkers. Just a little bit about myself. My name is Graham Mansfield, and I'm the Sales and Marketing Manager at Microconcepts. I've been focused on this particular product that you're going to see today since it's sort of been introduced into the UK, and it's quite an exciting, it's a really exciting product that sits on top of Autodesk Inventor. I'm aware that there's a number of people on the call today that are from either an AutoCAD LT background. There are some Inventor customers on the presentation today. So hopefully they're going to take some takeaways, but the message is pretty consistent in that you kind of need to move and transition to 3D first, and then with the woodworking add-on, the Woodwork for Inventor, then you're going to see some enhancements that basically deliver you the extra return on investment that you need to deliver things like bills of materials, etc., cutting lists, and more. So without further ado, let me just introduce you to the product. I mean, it was developed way back in 2012, and it's basically, I like to call it an out-of-the-box solution. The reason being is that a number of customers that take software today end up having to work out a workflow to meet their needs. The workflow is generally I guess orientated towards the woodworking industry, but traditionally, if anybody comes across the name Autodesk, everybody knows Autodesk, everybody knows AutoCAD. When Inventor gets introduced into companies, everybody kind of thinks that the Inventor is very much aimed squarely at the machinery and the manufacturing sort of industrial machinery space, when in real terms it's pretty generic. It covers a wide variety of different disciplines. So the Woodwork for Inventor software really, as I was saying, is an out-of-the-box user experience. It delivers, if you like, all the tools you need in the language of a joinery and woodworker to kind of to deliver the terminology and the results that you need. So we did, before we introduced it, we kind of looked at a typical designer's sort of typical working day, and we were finding that the 3D modelling with standard Inventor, on average, this is moving from, say, a 2D world of LT to 3D, was taking still about 40% of the customer's time, but we found that a whopping 60% was still based around creating those part schedules. We saw a lot of customers using Excel spreadsheets to kind of manage the project within the company. We also saw people using Word templates. They were kind of disseminating the information, and they were duplicating this information. They were looking at the drawings traditionally in 2D AutoCAD and converting this data, and they kind of carried on the same sort of in the same vein. They created 3D models, so they hadn't really moved on. You had the benefit of our parametric model that you could change, but they were still creating this manufacturing documentation. So it was a key challenge to kind of come up with something that would address this kind of area. And then those that actually moved to 3D were having problems where they wanted to know a workflow to define things like the material covers. So with a basic board, obviously, you've got different covers, a different fill, different edge that would be placed onto that particular board. And how would you report on that? And again, it was quite time-consuming to imagine kind of having to model all of this on every panel every time. So it was a key challenge in the workflow to kind of come up with a way of understanding what we needed to do to get this information out of the 3D model. So another area that was quite interesting was the problems of grain direction. So in a situation where we have, let's show this example, the model where we rotate the texture. Typically what happens here is that the size of the workpiece will need to increase to suit, and it's quite difficult again to get the bounding box to be reported with standard Inventor without some additional tools and maybe some more programming in the background. So customers were looking for this extra information. How would they adjust the texture and how would they extract that information? The other side of things is where you have these different size shapes that will be perhaps CNC machined, and everybody generates 3D models to the real world size, so that everything's actually spot perfect for the assembly. It's spot perfect for the final drawing and to get customer sign off, but the parts aren't optimized for manufacture, and that's a key point, and you're going to see later in the presentation. I'm going to take you through modeling, and you're going to be able to see how we can oversize parts. So this was a key area. Coming up with the final size, you need to be able to extend the part but leave it in its natural original state. So it's that core part that we want for manufacture, so we've got a starting point to report it down to the to production. And then another area that was, I suppose, quite important to realise is that placing hardware, ironmongery, into the model. Most companies would expect to be able to pierce the holes. They wanted a method of being able to add hardware like dominoes and biscuits and just general hinges, and make sure that when they're placed, not only are they visually correct, but to give an idea of actually putting the holes between multiple panels. And that can be a challenge in itself when you move to a 3D world, purely because there's multiple components. It's like dealing with the components on the shop floor, as it were, in the real world. So you want something that's going to basically equal the drillings, the pre-drillings. So all the pilot hole sizes need to be assigned. Any clearance holes that you need to be assigned can all be added into the hardware. So that was a challenge we had to address as well. And obviously you need to be able to then parametrically change your model and make sure that all this will update. And finally, getting this information out onto drawings. How would we dictate this in a drawing? And that was a challenge. So as I was saying earlier, a lot of companies use Excel spreadsheets or Word documents or some form of a template, a digital template to pull around the office. That information can contain a lot of part structure information. So you've got the edge banding information. So we need a way of actually extracting that information from the model. We need to be able to extract things like the oversize. So some companies will want to add the material to the overall A size there. Some people will want to remove it. So again, we need something that's flexible to be able to report on this. And again, when you're trying to create this component where we've got maybe the actual curves on the front face there, we'd want to add in additional material to just give that initial extra remnant to be able to be removed from the board. So with the Excel spreadsheet kind of concept, getting a list of parts, that's taken for granted. That happens with Inventor as per it has a standard bill of materials. But the crux of it is once you start to drill down, and you can get length, width, and thickness, but what you can't start to do is to start to report on things like the actual material covers, the edging that's applied, without having to model it. So we're going to treat each part as a single component, and you're going to see how easy it is to basically define that kind of structure of that part. Also, customers obviously need to know a little bit about the project as well. So there's facilities to be able to key in that information as well and pass that through to the spreadsheet. So another challenge customers have moving to 3D tends to be that if they move from AutoCAD, they're used to managing a single file. It's usually a single DWG file. If you're a competent user, you might have gone down the external reference way of working, where you have a file linked to a top file, and that kind of concept is kind of primarily how Inventor works. It has an assembly file, and then it has multiple parts. So you need a tool that will actually allow you to copy that design within the graphics window, and then be able to then go and change that into the next variant. Otherwise, if I was to change the component in one assembly, it would automatically update the component in the opposite assembly. So we just want to be able to basically pick and choose what size of drawer we require for our particular cabinet, as an example. So how does it work? Well, we've based the Woodwork for Inventor software on the core technologies of Inventor, because Inventor is kind of the market leader. It's fantastic for complex shape description, where you can pretty much do anything with Inventor from a 3D modeling perspective. But what it does lack is it does lack that additional information that you need to get out, which is the bills and materials, some form of automated drawing package, and potentially even CNC code as well. So we do have a module. It comes in a couple of guises. We have the Woodwork for Inventor package that we'll see today, but there is a Woodwork CAM for Inventor that is available to kind of process those panels if you haven't got any CNC software. So as we said, we can design any types of particular furniture with the package and assign any particular material. And the idea is to use this skeleton design approach. So we take a very rudimentary approach to modeling, which is fantastic when you're kind of massing out, or you're kind of providing space envelopes within a space, and then we then convert and turn that into a fully featured model. So the idea is, if we was to go back to the original skeleton and we change that, then everything will actually update accordingly. So it becomes a master, as it were, that drives the full complicated assembly. So I did allude earlier talking about parts, and they're actually drawn in their finished state. So we have a component like this, but what we want to be able to do is to split it apart, and it might be that the core is actually made up of as a multi-layer board, and we want to represent that in our bills of materials. So again, without actually modelling everything, it would be very difficult to do this out just with a standard seat of Inventor. And another great area is just things like adding material and taking material away. So a typical finger joint example here, these joints can be automatically assigned to the model, and effectively it's adding on that extra material and taking the material away from you. So it's always going to report on the true length of the part without having to worry about setting up complicated parameters that you might have had to have done in the past. So that's for the Inventor customers on the call today. So the whole model can be used as a prototype. So you could build a design, and then you can then make a variation of that design using the assembly copier tool that's built within the Woodwork software. So it's very quick and easy to make a different variation. When we take the bills and materials information from the model, what we're reporting on is the true thickness. So we've got the cover thickness, we've got the edge thickness that we can play around with, and we can predefine that. We can oversize and get that information directly from the model, and we can show texture direction in our drawings automatically as well. It will tell you whether the part's got grain or not on particular covers, so that's another unique. And the great thing is the template can be customized, so you don't have to be a programmer. It's fairly straightforward. We get a complete set of sample files that comes with the package. It's quite straightforward to be able to interpret those and copy and paste and integrate perhaps into your existing Excel spreadsheet. Or you can obviously create one from scratch, or base your new spreadsheet on the existing. So in essence, what we're talking about is reduction of manual calculations. It's basically to automate the process to generate this information for you automatically at a press of a button, which is ideally what's going to reduce your errors. So I did allude to creating what I call drawing bundles, automated drawing bundles. So they can be typically a single panel. So obviously there's lots of holes and cutout information and the edging information. So how would we display that? Well, we can have a grain indicator placed on the sheet. We can define the hole information, and we can then define the edging, and you can see it actually assigns the edge codes automatically on there as well. You can then see that it will actually apply a datum for you with the overall sizes, and that becomes a snapshot of that panel at that point. You can also generate an optional hole table, so by default it will place that on the drawing sheet when it creates it automatically for you, so you don't have to place it manually. And also there's a material legend that gets applied to the sheet as well, so that covers off the material code, what its material, the actual name of the part, etc., and the overall size parameters are passed to the drawing boarder. So you can see straight away we're talking about automating that kind of whole process. So without further ado, I guess I just want to introduce you to a quick demo. So I've broken this presentation using this desk into several key areas. And the first is just to kind of introduce you to modelling. So for those that use AutoCAD LT and AutoCAD on the call, the next portion is highly relevant. And then for the Inventor customers, if you just bear with me, just be about 4 minutes, we'll then start to move on to some cool technology to show you how to create the actual cabinets. So as I said, we're going to base it on the skeleton design. So we've got this kind of concept. So we need to build this skeleton. So you can use standard Inventor, and here you see on the screen it looks and feels a little bit like AutoCAD in the menu structure. And I'm just going to use the simple box command just to size up the overall size, and just going to give it a quick depth of about 850 there. So we've just defined a quick spatial envelope, and all I'm going to do now is to be able to start to modify this. So first thing I want to do is maybe turning it into a sort of a clear colour, and put some model edges on so we can see the part. And you can see that the interface is really intuitive. You can just draw just like in 2D, place dimensions just like in AutoCAD, but the difference here is obviously as I place these dimensions, the model sketch is actually updating. So this is the great thing of parametrics, and you can start to relate these dimensions to each other, which makes life very, very easy to go and change things. So again, the heads-up display, you can go and choose maybe a cut. We just say we want to move that extrusion through all, and it automatically knows it needs to do a cut. We've got some other cool tools on here, such as fillet. So we just put in a variable, and you can see there just by dragging the direction indicator, it's easy to change. So I'm just using a technique now just to remove some material, and I've just used a different thickness. What I need is an 18mm panels for the back, but I want the worktop to be physically 25. So I've got two material thicknesses there, but it's still one part at this stage. So this is just one approach to modelling. So now all I do is I just sketch on the faces, and I just create new solid bodies based around that particular shape. I can direct edit, so I need to bring the back further up, so I've just moved the back in by the material thickness. And you can see it's very quick and easy. You just sketch on the panel or that particular face, and then you can then just simply say extrude to the next face. Let's do the inside face here. So again, so we should have a few solids here. So we're finished with the solid one, but we've got the 3 solid bodies. And I'm just going to put in a simple rectangle sketch at the bottom here to denote the spaces of where those cabinets are going. We're going to put a work plane in because I want to extrude this particular profile. up to that work plane. If I change the position of that work plane, then the height of that unit will change as well. So you can see we're starting to automate and place a lot of information into a core model that will become the basis of the driving shape to drive the rest of the parts. So let's put the final, this will be the cabinet with the drawers. So we'll just place that in there. And I'm just going to change the actual material colour to a polycarbonate clear there. So all I'm going to do now is just drop in a simple support. So I need to support the top of the desk to the underside of the actual desktop. So I'm just using some tools here to constrain and make sure things are aligned centrally. It's all good practice to keep things centered up, but you're not limited to doing it that way. So you can see straight away I've just extruded that particular, or drawn that sketch of that rectangle, I've sized it, and then I've literally extruded it to the next face, the underside face of that particular panel. And remember, if I change the work plane of the height of the box, then it will actually update automatically. So the next process is to sketch on this back face here and just drop in a simple cutout just to give it a little bit of style. And you can see as I've been creating these dimensions, it's very quick and easy to kind of, if you've not done it quite right the first time, make a quick change as you go along. It's not a problem. Let's put some fillets on just to round off, put some nice radiuses in there, and it's pretty much done. So the next stage would be to kind of move into the browser, and as you can see I'm renaming the parts. So it's good practice to give it some kind of identity, and these parts will be created into solid assembly parts in a moment. So pretty straightforward. Nothing complicated about that. I'm just going to save it away. Just going to give it a name, and I think we're pretty much done there. So just to show you, if we change the sketch, you can see it updates. If we change it back again, the part will parametrically change. So this is a part. Now I turn it into an assembly. So I just need to choose a new target and make sure that all these parts are going to be placed into that folder, and it kind of looks exactly the same, but the difference is that each one of these parts you can actually switch off, or you can effectively edit in its own part window. So it means you can actually take that component and produce, if you wanted, CNC code directly from that particular component. So you just see, as I've been creating here, these are work planes, and I'm going to use these in my design in a while to place some hardware. So this is going to be my intersecting parts that I'm going to use in a while. So putting the work planes on the model is just a way of aligning where my connections are going to be in the future. But everything's on this source model. I think we're nearly done there. Just need to center that up. Good. So I'm just going to turn the visibility of those components back on, and I'll pretty much save it, and we're done. So that whole process there was something that you could actually pretty much do in Inventor LT if you wanted to. You know, we don't have the add-on doesn't work with Inventor LT, but that was a demonstration of what we call solid body modeling. It's not the only way you can create these models, but it's kind of the most efficient way we've discovered to generate this for you. So the next step would be for the Inventor customers to look at this iCopy design. So iCopy is a great way of actually placing these units into the model to give it a little bit more kind of automation. So we already have a predefined cabinet that we've modelled up. We're just checking the height that I need here. So I need to find out what particular height we're going to be dealing with, which is 625. I'm just going to go into the iCopy tool, and I'm going to go and find the actual case that I need. So here's the predefined case. So it's sized at quite a small size at this stage, and all I do is I literally assemble it using the sketch that you see here on the screen. So I just need to manipulate the view around, we just pick up on the corners and follow the prompts that it says constrain eye copy. It wants the front left point, the front right point, the back right point, and I'm just setting now the height. I can play around with the drawers, etc., and I'll be showing you that in a moment. But the great thing here is that it builds a complete copy of that particular design at the new size. So what we can do is we can actually put that in a user path. So we can go off. I'm just going to drop it into a new folder. And what we're going to do is we're going to name up the actual. We're going to put some prefix naming on it just to make the components unique. So in some instances you'll want to share components, and in some instances you'll want to completely replace it. So sometimes 95% of the components will be different anyway, and I'm just going to give this a quick prefix. So I'm just going to put in a G1 there. If I say OK on that, what it will do is it will actually go and create. So this is a process of creating those components at that point for that particular assembly, based on those parameters. And we just need to do the same for the opposite side. So very quickly we'll just go through, and this other one is a little bit different. This is the drawer case. This one's got some drawers in it, so it's already been pre-configured. And what we're going to do is we're going to play around with maybe make some changes on the drawers. So again, it's fairly straightforward. The process was select the left point in this example, which orientates the unit. It then sizes the unit, so we're just sizing the width. And now we're just going to size the back, so we just need to pick up on the back point. We could change the ball thickness as well if we wanted to. I'm going to play around with some of the drawn quantities. So every time you make a design change, it actually is updating that information. And again, we just want to put in the height there. That was 625, wasn't it? Yeah. So that will then build that assembly directly for you. Again, if you want to change the draw quantities, then again it'll just update those dynamically for you. So just going next, we'll refresh the graphics, and then again we're into the same dialog box, and it's as quick as that. I haven't found anything as quick to generate this information on the fly with this sort of technology directly, without having to drive things with complicated parameters. So yeah, it's pretty quick and easy. I'm just going to choose the temp case folder again. So that could be the folder that you're using on a particular project. And in this example, we're just going to, I'm not going to put a suffix on, but I'll just again put a unique GM on the front of that. And then it goes off and it'll build that assembly automatically for you. That's pretty much done. So I guess the next thing up would be to think about how we'd actually start to use some of the woodworking tools. So again, that's a little bit of Inventor technology based on that that kind of portion of the demo. The next up is to start to drill into the woodwork for Inventor. So let's look at the materials. Let's look at some covers and some edge banding. So what I wanted to do was just to say that we have different fill types. So these are like categories. We have a solid board or solid piece of timber. We have board. We have laminated board. We can make up multi-layer boards. We've got a type for desktops. And then the rod is any extrusion, any piece of architrave, any piece of aluminium extrusion. It's not limited to timber, but you know, it's basically giving you that ability to then split that information out into the spreadsheet. The final bit is the covers. So we address veneering, edge banding, and even painting separately within the package. And the fantastic thing is that we actually report this information differently in the spreadsheet. So we're actually giving a linear meterage for the profiles. Boards are measured in square meters, and solid timbers measured in cubic meters. So it's another way. Generally, you kind of set up that part type, and it's quite a manual way of trying to report this if you don't have these additional tools. So let's have a quick look at the woodworking. So it sits as a simple ribbon within the tool. So it moves from left to right. Let's look at the material assignments. So here they all are. So they're all in there. Laminated boards. We can go and find a particular style, so we can match it up. So in this case, I'm just picking the components in the graphics window. I could pick them from what we call the browser, and straight away you see it exposes the raw edge of that laminated board. If we wanted to have solid or just normal board, you could use that and then apply covers onto the core. So we could just use a piece of standard MDF. What we want to do is perhaps define the supports for the interconnections, and we'll just make those out of solid plastic. And then what we're going to do is just go into the edging. And again, the edging, you know, it can be different sizes and thicknesses. You can play around with that. And at the moment, I've got it to sync. It's syncing within the model, and we just literally whiz around the model, picking up these edges. And you can see it'll find the loops for you. And when we apply them, it's all good, and it's all applied. Let's have a quick look at the bill of materials. So this is a little bit different for those that are used to seeing Inventor. We actually have a BOM engine. It's a kind of a BOM specification generator. Drills into the actual database, finds the lengths, widths, and thicknesses, and then if you break down on each of these parts, you can see the cover information. So you can start to understand how we're trying to report this information directly from the system. So we might have a situation where we've got to oversize this particular board, so you can actually oversize specifically on an edge. So all we've got to do here is just literally set it up for, it's either covers or the core. So we've got the fill material, we pick the edge, and in this case, I'm just going to extend it by a particular size. And if you don't want it as big as that, you can just adjust it. So you've got apply for all edges or just one edge at a time. So either or. So we'll have that 25 on that side, and on the other opposite left-hand side, we'll have that 25 as well. So we just affected two sides. If we go to the bill of materials, you'll see straight away, if we drill down to that particular top, you can see now the length oversize that's been applied directly into the model. So again, we haven't affected the overall size of the part. It's still the finished size, but we're going to be reporting. We've given it some extra intelligence to be able to report on that down the line. So another key area that customers find challenging is placing a lot of hardware, and a lot of customers we've approached have said that they kind of leave it up to the production manager or the production department once the design's been created to work out how the parts are going to be jointed. And for those customers that have gone down the CNC route, that's kind of unacceptable. You've got to define up front all the screw positions, all the hole information, because the part that can then be read in directly into the CNC software and then processed. So we've got a situation where, if you recall, we placed the work planes. So what we want to do is we want to tie in those supports. So I'm just going to bring those work planes back, so you can toggle them on and off, and I'm just going to go and find myself the minifix joint. And all I do is I just follow the information. It just says this is a standard library component that comes with the software. We just choose the faces that we want to select, and it's placed those 4 minifix in there automatically. And if I just go through that process again, so we've defined the 2 nested boards, the internal face, and the 2 axis planes, and I get another 4 placed. Very quick and easy. We need to connect up the top to the side panel here. So again, in exactly the same way, I can just define, and I get another 3 placed in. So it's very quick and easy to generate this information. We've got some cool display tools in here, so you can just toggle to see the standard components within the assembly. And these parts are iParts. So for those that are familiar with iParts and use Inventor already today on the call, you should be familiar with this, but you can get up and change on the fly the particular components. So the situation here is you might just want to flip the orientation of the dowel, so the dowels are inboard, and we can use our iMatch tool to be able to then go and paste that information, a bit like match properties in standard AutoCAD. Pretty much done. So you can see very quickly it's quite easy to place hardware directly into the model, and then obviously that's going to be reported to you in the bill of materials specification. So that's shown directly with the blue definitions there. So if I just show you, what we can do is select a specific template. We can then define a name, and it actually then will strip out all the information from the BOM specification engine and populate a comprehensive spreadsheet for you. So this is using the standard Excel spreadsheet that comes with the software, and as you can see, it's reported on that information, and it's grouped into multiple tabs at the moment. So we've got say the complete parts list there. We've grouped into the laminated boards, the standard boards, the units. We've got a cutting list, and again it reports on the covers, and we're using codes to fill in this information, and again we're summating linear meterage for the edge banding, for example. Here you can put in customer name and information, so a really cool place to fill in this sort of information. And if I just show you another customer example of maybe a different style of report that we can get. So this particular report's been created to show the length, width, and thickness of material, but also we're reporting the thicknesses for the actual covers as well. So that might be a little bit more relevant. And again, you can have a separate sheet that just shows the ironmongery rather than trying to put it all on one sheet. It's really flexible, really easy to extract this information. You can have custom properties and develop this into a really comprehensive solution for the company. And then we get the situation where we've placed all that hardware into the assembly, and we need to provide the cutout information. So we have this fantastic sculpt tool that understands the difference between adding material and taking material away. So I'm just going to put in, this is a custom part, so I'll just put a couple of work planes in so you can see how to create work planes again for something on the fly. So I just need a couple of work planes there just to give me an intersecting point, and I'm just going to go and find an electrical USB power distribution unit. So just putting this Hafele unit in directly by selecting the top face and the two intersecting orientations for those work planes. So literally that's placed in there. So I don't put the hole in the panel, I let that unit put the hole in. And you can see that's the basic interconnection there with no holes in. So if we use the sculpt tool, what that does is it drills straight through the whole assembly, even those drawers with all their sub-assemblies, and drills every occurrence. Every time it sees one of our negative surfaces within the actual model, it will actually remove that material. If it sees a positive joint, it will actually add that material at this point as well. So you kind of do this towards the end of the process, towards after the customer's made his mind up as to it's going into production. And what we're doing here is, if we're doing this sculpt so we can show in our drawings the holes in the parts. So you can see straight away it's put all the hole information in there live for you. So it's really quick and easy. Obviously the more parts you've got and the more holes it needs to cut, the longer it's going to take. But you're just talking about raw computing power. It's as simple as that. And everything will be updated automatically for you should you want to make a design change. So I'm aware of the time. We're just moving on very quickly to the next part of the presentation, which is a quick in-CAD render. So anybody that's just using LT today might want to produce a quick render. And Inventor offers this fantastic, what I call in-CAD render. We can set to a realistic visual style. We can play around with shadows and ray tracing, and we can get some quite nice results. And it's up to you. You can wait a few minutes, a few seconds to generate this information, or you can, wait a few tens of minutes to create it. So depending on the quality that you're actually after. So you can see here, I think it is speeded up, but after about, I think it's about 39 seconds, we've got something that's kind of quite usable, and that's on the good option there. So obviously, you could just move it to the higher best option, and again, you can see how it works. The little pixels get finer and finer and start to diminish, but it will take a lot longer. And again, I have sped this little video up to, I don't want to be sat here for tens of minutes, but you get the idea. The longer you leave it, the better the image will get. And you can see some of the images in my presentation earlier today I've been using directly from this tool. So then the key thing here is to be able to create drawings. So in normal terms, creating drawings are by way of generating orthographic views. So you'll get the situation where maybe a customer will want to see a typical elevation type drawing, maybe an isometric view. They might want to have some dimensions placed on it, and you can do that with standard Inventor today. There's nothing I'm showing you in this little section here at the moment that isn't a standard part of native Inventor. We can actually balloon this information. We can actually place a parts list on the drawing as well, and we can actually convey very clearly and concisely what it is the customer's going to get, for them to enable us to kind of get that initial sign-off. And at this stage, the model can be very simple. You know, we don't have to create the sculpted holes. We can keep it in its basic form, and what we can do is we can then move this forward into the manufacturing information. So we've even got some section views we can create quite easily on the drawing. So it's really just to kind of give you a taster of for those people that are using LT today and AutoCAD, how quick and easy it is to create these views. But in essence, the crux of it is what do you do if you're a small joinery company where you've just got you haven't got any CNC machines, and you need to create kind of a drawing pack. You need to kind of tell someone exactly what it is that you're going to create. So we've got this auto plot tool. So the auto plot, we can predefine and pre-set up the views that we need to show in the drawing, and then what we can do is we can tell it whether we want whole tables to be placed. So we've got all the setting controls based within a single environment. We just choose the template we want, and off it goes. So just like cutting the holes directly into the furniture, what we're doing here is we're now creating a single sheet that is the assembly file, which is again optional. You could just create detailed drawings, and then it's going to create you a set of drawings in this example for multiple sheets. So you can see it's created that front view set up for us, predefined views. You can still go in and interrogate and create your own views to suit. That's not a problem. You can still manipulate the views. It's standard Inventor. We're just building on the standard core functionality of the standard Inventor engine. We're just automating some of this information. So you can see straight away here we've got a particular panel, and we've got some annotations on it. This is the worktop. It's cut the hole in for the USB power connector there, and all of this is actually defined directly in the hole table. So we just zip through all the different. This is one of the doors off of one of the drawers. It's got some paint on it, which it's showing on the code of 0.3. So that's the actual thickness of paint there. So very quick, very easy to get a drawing bundle out. So it won't apply to everyone that's using CNC machines, because they'll just want to take the 3D part. But it's a quick and easy way to get a complete snapshot of that assembly at that point in time of that design. And then just to wrap up, if you go and invest in the product design suite, which starts at the premium level, you get this fantastic showcase product, which is fantastic for customer review. So there's a slick workflow. You just go to the showcase button within side of Inventor, and then that then places that model, it ports it directly into Showcase for you. It just takes a few moments to load in, and then you can start to manipulate it. So this Showcase package is a way of showing in real time, without the clutter of a CAD modeler, the customer different alternatives and different comparisons. So straight away it pops in, which is a little bit of reorientation here, and we can change the environment that the model exists in, very quick and easy. And you can see straight away it casts different shadows, it ports different materials in based on what you have inside of Inventor, and again you can play around with the shadowing there, but it's all based on the lighting that's held within the environment. So I'm just going to cut in a moment to a more sort of finished example. So you need to spend a little bit of time just applying a few materials and maybe setting up some shots. So these shots are fantastic, where you can kind of tell a story. You can then basically toggle between these shots. So they're kind of pre-recorded little movies, and we can save this out. And I've got an example at the end of the presentation just to show you what can be achieved. I like this feature. It's being able to compare side-by-side customer examples. So in this, where the customers doesn't know whether they particularly like the drawer fronts, and they're umming and ahhing over particular colours, for example, you can play around with looking at different points of the model from different positions and reviewing different colour schemes. So that could be a different texture on the timber. It doesn't have to be specifically colours. It could be positional representations of where the if the drawers are open on the left-hand one and not on the right-hand one, for example. So you just play around with toggling the options there. So really easy to kind of review this in front of the customer live. So just to recap on some of the benefits of what you've seen on the presentation today, so we're pretty much nearing the end now. That's a few more minutes. We've covered off talking about taking the standard Inventor model, but addressing the materials, the edge banding assignment, looking at workpieces and creating size estimates where it considers the grain direction, fixture placement, so ironmongery being placed, doing pre-drilled information into the panels, automatic bills of materials, so we call it a BOM specification, directly out of the system, which is by far more comprehensive than you'll ever get trying to get Inventor to create that information. And then the drawing bundle, so using the auto plot technology can save you a lot of time. And if you wanted to, you can export directly to other nesting programs. So you can get a CSV file for, say, Magicut that you can then import to create your CNC information. So the time management kind of will reduce. So we were saying earlier, just to recap, 40% of the time is based on 3D modelling and 60% of the time is on preparing for manufacture. So using the Woodwork for Inventor add-on, you can reduce that. We've seen a compelling 30% and a big reduction on preparation. So it looks about a 50% time saving on creating this documentation and getting these models created as well. So automation is the name of the game. Being able to automate your design will allow you to reduce your errors. So reducing that interaction of human error can save you up to 80% fewer errors in your designs that we've seen out there. A couple of success stories, and again, it's working in real life, in action today at many companies. So just a couple of takeaways there, and got some examples to share with you. So it covers a wide variety. So generally, it doesn't have to be just shop sort of standard piece parts. It could be shop fit. It could be display equipment. This is an example of a jewellery display equipment case. Again, shop fit again. Furniture again. It could be door sets, so you could set up a parametric door set where the styles are changing on it, and then basically you'll get a new document pack every time to create all your piece parts. It could be staircases on the ornate style, on the traditional style. It could be wardrobe systems, again, fully detailed with drawer systems within. It could be again, unique pieces of furniture, desk systems, that sort of thing. And as you've seen today in the presentation. Also, you can even use it, we've got people considering for aircraft interior usage as well, because it's got a great way of defining the lightweight honeycomb structure that is used typically in aircraft interior manufacture. So yeah, it's got a place, and even you could take that analogy straight through for marine production as well. So design a complex, unique furniture, assignment of materials, visual material assignments, hardware assignments. We can do joint processing, automated BOM, and automated drawing generation. So that pretty much concludes my whistle-stop tour of looking at Woodwork for Inventor. I hope you've enjoyed your time looking at the product today. If you've got any questions, I'm happy to take those via email. I'll put my email up in a moment. If you want to learn a little bit more, I'll come back and we can have a phone conversation. Thanks for listening. And there's my email. You can get me at graham.mansfield@microconcepts.co.uk. Please reach out to me. I'll be happy to answer any questions you might have. Thanks for watching. Have a great day. Cheers now.